Yeah. It just, like it must have done an update and I don't know, like it doesn't look the same as this morning, so anyways. Also, it's showing all weird, but oh, whatever. Okay. So, last day I was trying to be a hero and get through chapter 3 without typing up the notes, because with typing up the notes I can go a little bit faster, right? Because we're not writing all these things down. But I should have known better. The whole goal is to get through 3.2 today, and it's not looking good, guys. So we're slipping behind pretty fast. So that's why I typed these up. And so last day we really only did page 1 and 2. But we can do a quick review. It was just the other day, so. And I also have, like I said, feast or famine around here. Didn't have enough. Now I have 3 extras from chapter 2. So if you don't have those notes from chapter 2, then you can grab them after class. All right. So let's see here. What are we doing? So last day we introduced, well, basically we were building up to the Z-score, right? And so we said, well, we're going to use the normal distribution to find areas under the curve because those are probabilities, right? And so that's what we're kind of working towards, using this normal distribution to find areas under the curve. In the end, we want probabilities, right? And so we introduced the 689599.7 rule, which is this fun to say rule. It is exactly what it says it is. So if you move out 1 standard deviation on either side of the mean, then you covered the central 68% of the curve, right, or 0.68 out of 1. 2 standard deviations, the central 95%. 3 standard deviations, you've covered basically all of the curve, right, 99.7% of it. Right? There's still some area in the tails, right? But 3 standard deviations, you've covered basically all of the curve. Okay. So once we have this approximation, 68, 95, 99.7 rule, we can use that information to find things like, okay, well, what's the area in the tail from 1 standard deviation below the mean, for example. What you'll find is that we're often more interested in the areas in the tails, right? What's the probability of seeing something more extreme than this? Right? And so we can kind of work with them as puzzle pieces, and I can't go into it more now, this is a review. But then we developed this idea of, okay, so if we know this fact that if we move out 1 standard deviation, 2 standard deviations, 3 standard deviations, then we can approximate the area under the curve, then it's helpful to know how to calculate, well, how many standard deviations is that from the mean? And so we said, well, if we had to just kind of brute force it, we would find the distance between these 2 points and divide it by whatever the standard deviation is worth. Right? And that's where we developed the formula for Z. Right? So Z is the observation that you're interested in, X, minus the mean over the standard deviation. Really, the distance between X and mu over the standard deviation. And that's on your formula sheet. And then we ended here-ish. And we said, well, then we can calculate the Z-score for an observation of -4.91, for example. How far is -4.91? From 6 if the standard deviation is worth 2. And we said it's 5.455 standard deviations below the mean. Right? So a negative Z just means that it's below the mean, and a positive Z means it's above the mean. So all those are on here. I'm not going to do example 4. You can try it on your own because we'll do more examples of it in a little bit here. So these z-scores, they have their own distribution. We'll call it the z distribution. Sounds reasonable enough, right? Z-scores are standardized values. And so we use z-scores so that we can compare an observation from one population where the mean might be 1 and the standard deviation is 2. And then we have another population where the mean is 20 and the standard deviation is 3. We can standardize those and look at, well, how does this observation compare to this observation, right? So we're able to standardize these values. First breath. Okay, so the Z distribution has a set of properties. Okay? It's going to be a normal distribution, which kind of makes sense because we're taking our observation from a normal distribution and we're just shrinking it down. Okay? Z has a mean of 0, and that's always true for Z. Okay? And a standard deviation of 1. So we take our old distribution, right, whatever it is, whatever the mean and the standard deviation are, we shrink it down to this kind of miniature normal distribution centered on 0 with a standard deviation of 1. Okay. So we can use some notation. Okay. Just highlight it here. Or talk about it. So these facts, Z follows a normal distribution, Z has a mean of 0 and a standard deviation of 1. That's a lot to say, right? And so we can summarize that with this notation. So how you're going to read this is that Z follows up. So the tilde you read as follows up. Capital N stands for normal distribution. And with a mean 0 and a standard deviation 1. Notice what we're doing here. Shape, center, spread. Right. So it's got all the things that we need to describe the distribution fully. Right. And so I've seen often people get confused and try to plug in a value for n. That's not going to be the case, right? So a lowercase n, yes, is the sample size, but an n in this case just means normal distribution. Okay. And I'll just put a little arrow. So the follows is the one that throws people for a loop, the little tilde. It's just shorthand for follows up. Okay. That's nice and condensed. So in general, any distribution of x, we can just write x follows a normal distribution with a mean mu and a standard deviation sigma. So, any questions before I blab on? Carrie? Yeah. So, knowing that Z has a mean of 0 and a standard deviation of 1, well, first of all, does it make sense for Z to be centered on 0? If you think about, so any mean is 0 standard deviations away from the mean, right? Hasn't gone anywhere. So that's why it gets boiled down and centered on 0, right? And then we go out by 1 standard deviation. So we can revise the 689599.7 rule and apply it just to Z-scores because now it'll be easier to talk about. Right? So between a Z of -1 and 1, you have an area of 0.68 or 68%. Right? Between a Z of -2 and 2, right? 2 standard deviations, 95%. -3 and 3, 99.7%. Right? And so it makes it a little bit easier to work with, but also to use. Okay. So, for example 5, nice. What's the probability of an observation being less than 3.4 if the mean is 5.3 and the standard deviation is 1.2? Okay. I'm asking for the probability, which is the area under the curve. And the one that I'm interested in, knowing the probability of, is 3.4. So that's what makes it X. So here we've got X. The mean is 5.3, so that's mu. And the standard deviation, 1.2, is sigma. Oops. Jump the gun here. So what I would do, and what I've drawn here, but we'll draw it together. You always want to sketch out the area that you're looking for, right? So when you read this question, you're going to think, okay, well, I guess we're assuming it follows a normal distribution. It will, it'll always follow a normal distribution. Okay. When I give you the mean and the standard deviation, you can assume it follows a normal distribution. So what we're going to do is, right, we're going to draw our normal distribution, and in the center, down the center, you're going to put your mu, which in this case is 5.3. And then somewhere, it doesn't really attach anywhere on the graph, but somewhere kind of close to here, I'm going to put the sigma as 1.2. And that's just because I want to have it close by, right? So it doesn't go anywhere, but just write it down there. And then the number that we're interested in is 3.4. So one thing to keep in mind is that down here on this axis, you have just a number line, right? So 3.4 would go to the left of 5.3, and anything above 5.3 would go above it, right? And so it's just a number line. We just draw these just to get an idea of what we have to do, right? So kind of making a plan of attack, I guess. So I just draw a line anywhere, as long as it's on the right side of the mean, right, correct side of the mean, then you're okay, right? So 3.4, that is the number, yeah, would go somewhere below the mean, right? So I don't want you to spend a lot of time trying to figure out, where would 3.4 fall, because that's way too time consuming. And the whole idea is just to visualize which area you might need to answer the question. So as long as it's kind of below, I tend to just put them in the middle somewhere, right? Even if you think it's going to be super close, putting it here makes it a little bit confusing. So just kind of plop it in the middle, see what happens. And then I shade in the area that I'm looking for. In this case, we want to know, what is the probability of an observation being less than 3.4? So the probability of being less than 3.4 is all of this area. Right? So that's the area that you're looking for. I could just as easily ask you, what's the probability of being greater than 3.4? Then you'd have to find this area. Questions, comments, concerns, complaints? I just added that fourth C the other day. I think it's catchy. So I've calculated the Z for you, but just so we can go through the motion, let's just calculate it again. So I'll just plop it in here. Because what we're going to do, right, is we know the 68, 95, 99.7 rule. And so one way or another, we have to find how many standard deviations is 3.4 from 5.3. If the standard deviation is worth 1.2, no matter how you do it, you are going to calculate a Z score. So you may as well just call it a Z score. Right? So Z is X minus mu over sigma. .4 minus 5.3 over 1.2. And I'll just skip to it. It's negative 1.583 repeating. So what we can do, just use a different color here. Now we can redraw our normal distribution. You don't have to. This one's extra just to prove a point. Okay? So Z, right, what we're saying here is that an observation of 3.4 is a Z of negative 1.583 repeating. Right? And Z follows a normal distribution centered on 0, right? 5.3 is 0 standard deviations away from 5.3. And so now we can redraw this curve, but just kind of shrink it down to the Z curve. But they will be the same. So for Z, Z is centered on 0, and the standard deviation is 1. And this value be somewhere here, negative 1.583 repeating. Something's going on with the projector. It's not showing my awesome colors, but whatever. Doesn't matter. So here, this is still the area that we're interested in. This is where we run into problems with the 68, 95, 99.7 rule, because we can use that to approximate the area, right? We can use it to approximate this area because negative 1.583 is between negative 1 and negative 2. Right? And so those are the only cutoffs that we know. We know 1, 2, 3. That's it, right, so far. And so that's fine. We can just say, okay, from negative 1, we know the area in the tail. And from negative 2, we know the area in the tail. And this area must be somewhere in between those two. So let's start, whoops, with negative 1. If we imagine, right, between negative 1 and 1, by the 68, 95, 99.7 rule, right, we have 0.68 in here, which means we have 32 or 0.32 left over, but we have to split that evenly amongst the tails. Right? And so really what we have here is 0.16, and then here 0.16 as well. Oops. 6 got out of control there. So you can use this rule to find these tail probabilities too. And that's because of symmetry, they have to be the same. So by the same logic, we know that between negative 2 and 2, right, we've got 0.95, And so then we've got 0.05 left over, which we have to split evenly amongst the tails. So we've got 0.025 on either tail. I'm not putting it on all on here because it would get too messy. But you can kind of work through it the same way that we did with the 68, go from 95, right, figure out what's left over, split it evenly amongst the two tails, and you'll end up at 0.025. Something about this, so it makes sense, right? So I think we're all convinced that, yeah, this area is somewhere between this area and this area, right? But it's a little bit unsatisfying to be able to report back, well, the probability is somewhere between 0.025 and 0.16. That's not that great, right? I'd probably say, can you give me a more accurate number? That is accurate, just not very good, right? And so here, but it's a perfectly good approximation, right? Because it's true. This probability, right, this area is between 0.025 and 0.16. It's just, we want a little bit more precision. Right? And I think I foreshadowed a little bit last day. That's where the Z table comes in. Right? And so we'll have a look at that. But yeah, we could just end up saying that the probability is somewhere between 0.025 and 0.16. We could do that. We won't. We'll use the Z table. Yeah. It's like I wrote these notes. I did. Just yesterday, in fact. Although this approximation works, right, like we established, we'll want to find more precise probabilities. Okay? So to do that, we're going to use the Z table. Okay. Your Z table, does everyone have their formula sheet with them? I brought some if you need to borrow one, or if you never got one, you can have one. Does anyone need one? So the Z table, well, it's the first table after your formula sheet. And if we just kind of flip through it, don't look too closely. You'll go cross-eyed. There's a negative side and a positive side, right? So it starts with the negative side, and how you're going to find it is just looking at the left-hand margin, and then there's the positive side on the other side. Okay. And so I'll just talk about the steps, and then I'll show you, because I've got it. You know what? I'll just pull it up on here, because I'm that prepared. So table A, I'll just call it the Z table. It is a Z table. You've got Z's here. And so what it's doing is, instead of just having cutoffs at -1, -2, -3, which we had, right, it's moving in increments of, well, the second decimal place at the hundredths. Sold. Pretty sure. Tenths, hundredths. Doesn't matter. So it can get really nitty gritty, right? So for a Z to 2 decimal places, and how it works is you have your whole number and your first decimal in the left-hand column, okay? And these are all Z scores. And then you're going to join it up with a second decimal up top. Okay? So when you join these up, you're going to land on one of these numbers. Okay? And what these numbers are, they're just areas to the left. Okay? So So how it's going to work is you feed it a z-score, and it spits out the area to the left. Okay. Just like complements work, right? If you know the area to the left, and we know that the total area is 1, I give you the area to the left, you know the area to the right. Right? So it only has to give you one side for you to know both sides. That's nice. It's a huge table anyways. Okay. And so if we scroll through here, what it's doing is it's moving from negative 3.49. It's the largest negative value. Okay. And then it just moves in tiny, tiny increments, and it's just giving you the area to the left. Right? So as it's moving closer and closer to 0, the probability at a z-score of 0, we're expecting to be 0.5. So if we go here to a z of negative 0.0, there is no negative 0, but they had to do it on here to complete the table. It's going to be 0.5. And then if you flip it over to the positive side, oh, I'm doing it on there, but I should do it on here. Now we're over on the other side of the mean, where all our z-scores are positive. Right? And so now we're moving from 0. Now all these probabilities are going to be bigger than 0.5, right? Because it's still giving you the area to the left as you move further and further out. One thing that's going to be important is that the z-table only has 2 decimal places, right? It can only handle 2 decimal places. And so you're going to have to round your z-scores to 2 decimal places properly, right? And so even if you don't remember to round your z-score, when you go to the table and you think, oh, wait, it only handles 2 decimal places, then you can go back and round your z-score to 2 decimal places properly. And then you'll be able to find the area to the left. Any questions about that? Okay. So we'll come back to that one. But I just wanted to make a note here, because I have it there. Calculate the z-score. So that's your first step, right? To finding these probabilities, we have to find a z-score first, right? And then we're going to round z to 2 decimal places. And that's just because it has to match the z-table. Need to match the number of decimal places in the table. Need to match the number of decimal places in the table. I guess I usually do step 2 first. I draw the normal curve to kind of get a handle on what I know, what I don't know, what I'm looking for. Right? And so I know drawing the normal curve isn't going to come naturally in the beginning, right? But I can guarantee you this, towards the end of the course, you'll kind of be relying on these normal distributions. Okay, let me just draw it out. So it's good to get in the habit of drawing them out every time, even if it doesn't make sense to you right now, right? It will be a really good tool for figuring out what you have, what you need to do, how to get there. So calculate the z-score, round it to 2 decimal places, and then go to the z-table and find the whole number and the first decimal of z in the margin on the left. Notice there's a negative and a positive side of the table. That's all good. And then join it with the second decimal in the top row. And then the table entry, so those are the ones in the body of the table, is the area to the left. So in our little example, we had a Z of negative 1.5833 repeating. So if we have to round that to 2 decimal places, right, we're at negative 1.58. So let's find the area to the left of negative 1.58. If you go to your table, okay, so we've got a negative, so go to the negative side. And then we've got a Z of negative 1.58. So here and over here. And so you have to be kind of careful. Your eyes will play tricks on you. It's almost as bad as the boop 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 method. But it still works. Okay. Join these up and you'll land on 0.0571. So that's telling you that the area to the left of Z of negative 1.58 is 0.0571. And I've got those steps in here. My negative 1.5, join it with 8, and then we find that they meet at a value of 0.0571. So from that, right, we can say that the probability of an observation being less than 3.4, the mean is 5.3, the standard deviation is 1.2, just in case you forgot the question, is 0.0571. If you look back here, so what we're saying is that this area is 0.0571. That is between 0.025 and 0.16, right? That's true, but it's way more precise, right? So even though that's not going to fail you, right? But the Z table is the way to go if you want more precise values. Or if you want to kick it up a notch, norm command in R, and it takes the X value, it takes the mean, and it takes the standard deviation. Notice that this value is a little bit different, right? We had 0.0571, here we get 0.056677275. Looks more precise, and it is, right? Because we had to round our Z score to 2 decimal places, where it's able to keep all those decimal places. So that's where it's even more precise. So here, this is X, this is mu, and this is sigma. And just like before in these notes when I type them up, I just want to have these commands so that you can look at them and kind of make the connection. It's not something that I'm going to test you on. Okay, so don't worry about that. Just good to know. Just so we can get in the habit of drawing out these values. Normal distribution centered on 0, negative 1.58. The area to the left was 0.0571. Any questions about that? It's new, it's weird, but we'll be using it a lot, so you'll get used to it as we go. Okay. In our previous question, right, the one we kind of started with for the Z scores, we had a Z of negative 5.455. If we tried to use the Z table, what you would find is that, like I said, the largest negative value on here is negative 3.49. Right? That's as big as it'll go in either direction, right? That's the same on the positive side. Right? And so if we're looking for something like negative 5, right, all we can say is that, well, that's beyond this point, right? Negative 3.49. Negative 3.49 has an area in the tail of 0.0002, tiny. Right? And that's probably why they said, oh, we're just going to stop calculating these here. That's small enough. We can just say approximately 0. Okay. So that's the trick. If you go beyond the table, right, in either direction, so negative 3.49 or 3.49, you find something beyond that range, you can just say that the area in the tail is approximately 0. Okay. It's important that you say just approximately, because remember what we said, these tails never close on the axis, right? And so there's always a probability of something happening, right? And so the probability is never 0. It's approximately 0, close to 0, but it's never just 0. It's like Dumb and Dumber. When he's like, so what are the odds of us hooking up? She's like, about 1 in a million. And then he gets all excited because he has a chance. So it's the same deal, right? So these here never close, and that's just leaving room for anything can happen. Whatever his name can date, whatever her name is, Swanson. Samsonite. We used to watch, my parents are so weird that way, so we didn't know English yet, but they would let us watch Dumb and Dumber. And so we watched a lot of Dumb and Dumber without knowing what they were saying, or, yeah, anyways. Important part of my childhood, I guess. Oh, so here, I have a note on, right, if we find z scores beyond plus or minus 3.49, beyond the table range, we can say that the area in the tail is approximately 0. Technically, we would say that it's less than 0.0002. Did I throw too many zeros in there? But approximately 0 is easier. And then I have a little, very important, that we don't say the probability is 0 because it's never 0. And if you tell me that a probability is 0, I'll have to take marks off. That's bad. Okay. So we can use the Z table to find probabilities, right? Or if we kind of rework it and work backwards, then if I give you a probability, you can work backwards to find the value of x that makes that happen. For example, the grades had a mean of this and a standard deviation of this. What grades were in the top 10%, for example? Bottom 20%, that kind of thing. Right? And so now I'm giving you a probability, right, or a percentage or a proportion, and so you can work backwards to find the value of x that makes that happen. Right? And so I kind of think of it as a pendulum, right? And so you can start with an x. So that's what we've been doing so far, which you're going to morph into a z, which then you can use to find the probability. You get from an x to a z using z is x minus mu over sigma. And from a z to a probability using the z table, And we can work the other way, just the same, right? If I give you a probability, using the Z table, you can work back to a Z-score. And then from a Z-score, now that you know a Z-score, and you know mu and you know sigma, you can solve for X. And that's how you're gonna get here. I call it working backwards, probably because we start at X and go to a probability, and then now we're working backwards. But so it's kind of a two-way street, if you will. Okay. But it's always a two-step process. Right? I've seen a lot of the time people want to skip the Z-score, just go straight to the probability, but that's not going to work. Right? Okay. Questions? Ready for an example that I stole out of a Canadian textbook, but they still use ounces? Weird, right? A cereal manufacturer has a machine that fills the boxes. A serial killer has a machine that fills the boxes. No, it doesn't work. Boxes are labeled 16 ounces. Okay. I think we all understand that when we go to the vending machine, for example, and we get a bag of chips, it'll say that it weighs some amount, but we all understand that it's not going to weigh that exact amount, right? A little bit less, a little bit more, but we are expecting it to weigh around that, right? And so that's a problem that we have everywhere, right? So regardless of what you're producing or doing, right, there's going to be variability no matter how tiny, right? And so in this case, right, if we have a machine filling these boxes and we set it to fill at 16 ounces exactly, right, on average, then half of these boxes are going to be less than 16 ounces. Just because of, if you're forcing the mean to be 16, then just by properties of the normal distribution, half of them are going to weigh less than 16 and half of them are going to weigh more than 16. Right? So what we do is we set it to be something a little bit higher, right? Shifting that distribution over so that you've got more boxes being filled at least 16 ounces. Right? And so, oh yeah, if the machine is set at exactly 16 ounces and the normal model applies, then about half of the boxes will be underweight, making consumers unhappy and exposing the company to bad publicity and possible lawsuits. Dun, dun, dun. I just thought that part was funny. I thought about cutting it, but it is funny. It's like, this is serious stuff. So to prevent underweight boxes, the manufacturer has set the mean a little higher than 16 ounces. So based on their experience with the machine, the company believes the amount of cereal in the boxes fit a normal distribution, of course, with a standard deviation of 0.2 ounces. The manufacturer decides to set the machine to put an average of 16.3 ounces in each box. Okay, so they've shifted the mean to 16.3, right? Aim for 16.3. We understand that there's going to be a standard deviation of 0.2, right? So some wiggle room. Now the question is, well, part A, what proportion of boxes will be underweight? Underweight in this case is anything less than 16 ounces, right? Because the consumer is expecting 16, right? We understand if it's just a little bit less than 16, right? But as a manufacturer, we want to go, okay, 16, that's underweight. We can't be selling that, right? And so we need to know what proportion of the boxes will be underweight. Here, let's remember, so the 3 P's are all the same: proportions, percentages, probabilities, right? all these p's, so a proportion is a probability, which is essentially a percentage and all of these are areas under the curve. So it doesn't matter what word we use there. The goal here, I'm asking what proportion of boxes. So I want to know the area under the curve that satisfies this underweight criteria. So part A, if we start by just sketching it out, right, get a lay of the land here, we can start with a normal distribution. And we're told that, I'll just put it here, mu is 16.3 and sigma is 0.2. That's all the information that we're given. So we can just start by jotting down that information. And it has nothing to do with the question. This will always be the case, right? Follows a normal distribution centered on 16.3 and the standard deviation is 0.2. So 16.3 and sigma is 0.2. This is a little bit sneaky, right? What proportion of the boxes will be underweight? It's kind of implied, right? Underweight is anything less than 16 ounces. That happens a lot where we're supposed to take some piece of information and just kind of make it into a number, right? Underweight 16. And you just kind of have to think about it, I guess. I try not to do it too much because I know it's hard. So 16 is less than 16.3, so I'll just plunk it down here. And we want to know what proportion of the boxes will be underweight, right? So less than 16. And so the area that we're interested in is this area here. So I'll just put a little question mark there. Okay. Next thing we're going to do is we have to find the z-score, right? So our x in this case is 16. We want to find the z-score. Then we can use the z-table. So I'll just kind of call it the first step here is z is x minus mu over sigma, which in this case, oops, is 16 minus 16.3 over 0.2, which is negative 0.3 over 0.2, which is negative 1.50. Just so I can have all this answer on the same page, I'll just put step 2 over on this side. I'll need more pages though. So now we know that 16 is 1.5 standard deviations below the mean of 16.3. So now we have the z-score. It's already 2 decimal places because I forced it to, right? It's actually negative 1.5, but then I just tacked on a 0 just to emphasize 2 decimal places. So you always have to shrink it down to 2 decimal places, or in this case, build it out to 2 decimal places. Okay. So now what are we going to do? We're going to go to the z-table. And we have to find negative 1.5 here. We've been here before, but now our second decimal is just 0, which is this first column. So the area to the left is 0.0668. So here's where I'm going to give you a few options for writing out this step. Okay. What I want you to do, though, is communicate what you just did. I'll start in words, and then I'll show you probability notation in case you want to use it. Okay. I stick to just the words because it makes sense to me, right? Well, probability notation makes sense to me, but it's helpful because I'm explaining exactly what I'm doing. Right? And so these are your only two options. Right? And it's going to feel very tedious, in fact, in the beginning. But there's so many places where you could go wrong. So it's better to just adopt this sentence structure or probability notation if you prefer, and just stick with those. Okay? Then I'll show you some stuff that I don't want to see in a little bit. So all I end up doing is just writing out exactly what I did. So using the Z table, we find the area to the left. Of Z equal to negative 1.50 is 0.0668. I'm just writing out exactly what I did and what I found. Tedious, yes. Accurate, yes. Or, if you prefer, you can use probability notation. It's going to be shorter, it's going to be quicker. The probability that Z is less than or equal to negative 1.50 is 0.0668. Both of these communicate the same information, right, properly. So therefore, the proportion of underweight boxes is 0.0668, because that is the area that we wanted, right? The area to the left is the area that we wanted. So we're done. If I had asked what proportion of boxes are not underweight, then we would have had to find this area, right? 1 minus 0.0668. Yeah.
Less than the
No, because we went to negative 1.5. Yeah. It's actually the way they work, it's not important or not critical. But in this case, it's equal to. So, right, so it depends on the information that we were looking for. In this case, we were looking for this area, and that's what we found, so we're done. And just to emphasize it, I'll draw it on here. Oh, I should use a different color maybe. It is fun. Exactly that fun. So therefore, the proportion of underweight boxes is 0.0668. just gonna sneak in some blank pages here. Add a page. I know. It's BYOP around here. Bring your own paper. So, part A, not bad. I'm gonna take that for this. Great. Even if it wasn't. I show you these two ways because there are some key things that I don't want to see. So do not write something like Z is negative 1.50, which is 0.0668. There's no universe where negative 1.5 is 0.0668. I know what you mean. That's the problem. So of course I know exactly what you mean, right? But that's not true, right? And so you want to be careful with, especially with equal signs, because I'll be a stickler with them. Okay? That's not true. Right? If you try to tell me this, I will have to take marks off. That is true. Okay? Even something like, even if you tried to tell me that Z is 0.0668, that's also not true, right? So I don't want to see that either, right? That's not true. Z was negative 1.50. The probability of being less than Z, or the area to the left of Z, of negative 1.50 is 0.0668. So of course, I know what you mean, right? But you're not saying what you mean. Right? And so I want you to stick to either of these options, whichever one you're more comfortable with, right? I tend to do this one. Right? It's a little bit more tedious, but it's nice and safe. All I'm doing is just explaining exactly what I'm doing. Right? And so, or this one if you, I don't know, prefer that. Okay? So just be careful. Any questions about that? Great. Let's do part B. What proportion of boxes weigh more than 17.21 ounces? So now we're on the other end, right, on the high end, and we want to know what proportion weigh more than this. Okay. So part B. If we sketch it out, we can sketch our normal distribution again. It's still centered on 16.3 and sigma is still 0.2. But now we're interested in 17.21. So 17.21 would go somewhere above here. Even if I suspect that it would be further out in the tail. Remember, the whole idea is just to visualize the area that we need. And so I'm going to put it here, 17.21. And we want to know what proportion of boxes weigh more than 17.21. And so this is the area that we want. Put a little question mark there. Same steps. We're going to find the Z score, use the Z table to find the area. The Z table is going to give us the area to the left, right? But we can use that area to find the area to the right. So, nothing to it but to do it, guys. Let's see here. Step 1, Z is X minus mu over sigma. Here, our X is 17.21 minus mu, which is 16.3 over 0.2. We have 0.91 divided by 0.2. 4.55. Okay. Okay. We already talked about this, right? So now we're kind of, I'm just illustrating a point. So we can go to our table. Right now our Z's positive, and so we have to be on the positive side. And we try to scroll down here. I'm at the bottom. Yep. And it maxes out at a Z of 3.49, just like we talked about earlier. Right? And the area to the left is 0.9998, making the area to the right of 3.49, 0.0002. We also know that because of the symmetry, right? So we can go back here. And say, okay, well, we've got, if we sketch it out quickly, Z is centered on 0 now. Here at 3.49, we can say that the area to the right is 0.0002. Remembering that this is still just a number scale, if we plunk 4.55 down, we can see that, well, the area in the tail of 4.55 is just less than this, right? So we could get technical and say, well, all we know is that the area is less than this, or just jump to it and say it's less than 0, or less than 0, no, approximately 0. You said, I know. So, I was going to write out the one that we could say, but I'm going to skip it because we're not going to say it. The probability, I guess this is step 2, of a Z larger than Z equal to 4.55 is approximately 0. Or if you prefer, the probability that Z is, I'll say greater than or equal to, just because it doesn't really matter for this, 4.55 is less than 0.0002 or approximately 0. Okay. Again, it's going to be important that you do the squiggly equals, right? Approximately equal to, and not the hard equals, because 0.0002 isn't equal to 0. It's approximately equal to 0. So again, just emphasizing that. Therefore, the proportion of boxes weighing more than 17.21 ounces is approximately 0. Oops. Put in another blank page here. Oops. So well, any questions about that one?
So if your Z score is a negative number, you just take whatever this number is on the table, but then if it's
Yes, if you're looking for the area in the tail. It just depends on which area you're looking for, right? Because if you go to 3.49, it'll give you 0.998, 998, which makes the area in the tail 0.0002. Often what you'll find is that we'll be interested in the tails, right? And so we'll get used to doing this. Another trick you could use, right, is even if you want the area in the tail of a positive number, instead of doing 1 minus the area to the left of it, you could just by symmetry say, well, I could just find it for the negative and the area in the tail will be the same. Right? And that's where that symmetry thing comes into play. But you don't have to worry about that. Just if you wanted to. Ready for part C? What would I do if you guys said no, we're not ready? I don't know. Ready or not, here we go. What proportion of boxes will weigh between 16.11 ounces and 16.61 ounces? So, all right. Fair enough. Let's just draw it out. So we've got 16.3 in the center. Sigma is 0.2. Same idea. We're just going to draw out the area that we're looking for, right? And so 16.11 is to the left of 16.3. And 16.61 is to the right of 16.3. And the area we're looking for, can just shade it in, is this area. Okay. As long as we remember symmetry and that the total area is 1, there's lots of ways that we could find this area, right? We could treat them as just little puzzle pieces, and whichever way comes naturally to you, do that way. For me, I like to find, right, because the Z table gives me the area to the left always. So what I do is I just find the area to the left of this one, and then I find the area to the left of this one, and I subtract it from this bigger area, right? And so that's the same as taking this puzzle piece and lobbing off that tail end to get this area that I want. Another way you could do it is say, well, okay, I want this area. I know the total area is 1. So another way I could do it is just find the tail bits, lob them off. By that, I mean subtract them from 1. So you're left with the area that you want. You could do weird things. Not sure why. Need more work, but you could do weird things like find this area, add it to this area. It's harder. You don't want to do that, but you could. You get to the same answer. Right? So there's lots of ways that you could do this and find this. So whichever one comes kind of that you see right away, that's the one you should stick with. As long as you can explain to me what you're doing, right, it's fine. So, like I said, we're going to work with these individually, right? So I'm going to find a Z-score for 16.61 and use that Z-score to find the area to the left here. And I'm going to parking lot it. And then here I'm going to go and find the Z-score for 16.11. Go to the Z table, find the area to the left. And then I can bring this bigger area back and subtract the smaller area. Just like that. I'll be done. Racing the clock. Okay, here we go. What I'm going to do, just so you can generalize it for later when you're doing these problems, is I'm going to call this this little guy the lower, and this one the upper. Okay. You could specify them by 16.11 and 16.63 or 16.61, but now when you look back and you say, okay, there's a lower and an upper, hopefully it'll make more sense. Okay. So my first step is I'm going to find Z upper. Doesn't matter the order that you do them in, but I like to use the same order always, right? I find the Z-score for the upper, find the area to the left of it, find the Z-score for the lower, find the area to the left of it. So Z upper is X minus mu over sigma. X in this case is 16.61 minus 16.3 over 0.2. I don't have these. Thanks. Wait, no, some on the upper one.
Oh, the upper one is 1.55.
Thank you. 1.55. Sort of pre-cooked through Dimitri. So, step 2 that I'm gonna do, if you want, you could just find the Z scores first and then use the Z table, but it's nice to mix things up. So now we have a positive Z score of 1.55. So going in here, we've got 1.5 and then join it up with 5. 0.9394. So I'm just going to write that out in words. Using the Z table. So far, so good. Yeah. You'll have to find the areas. Yeah. Like, could you do Z upper?
And then get the.
No, I don't think so. Yeah. No, I don't think so. I'd have to check, but I don't think so. Using the Z table, we find the area to the left, of Z equal to 1.55 is 0.9394. Already forgotten it. Is that it? It is. Phew. So now just put that to the side. Right? Now we're going to find Z lower is 16.11 minus 16.3 over 0.2, which, oh, I'm skipping steps, aren't I? Negative 0.95. Bless you. Step 4. Using the Z table, we find the area to the left of Z equal to negative 0.95 is what? What was it?
Oh, yeah, it's to the right.
Because what I'm finding, right, is, so this value here has a Z of 1.55. So the Z table always gives me the area to the left, right? If you wanted to, you could find the area to the right. Lob it out the 1, as long as you did the same on this side, right? But what I'm gonna do is I'm gonna find this area, right, and then subtract this area. But yeah, you could go that way too. Okay, whoosh. So what is this area? Negative 0.95, 0.1711? Therefore, the proportion of boxes weighing between 16.11 ounces and 16.61 ounces is 0.9394. That is the number, yeah? Yeah. Minus 0.1711. 0.9394, whoops. Minus 0.1711. 0.7683. Done. We'll finish the rest on Monday, obviously, but maybe take a stab at them. See how they go. But you don't have to. Make sure you've handed in assignment 2 if you didn't already. Otherwise, see you guys on Monday. Thanks.
Just borrow this for a minute.
You bet. Oh, nice. Thanks.
Would it be okay to write it like this?
The probability that
I just
Z
subtract them.
is less than. Yeah. That works.
Okay.
Mm-hmm.
And then
Cool.
for this one, I'm pretty sure it should be greater than because
It
let's say over, and also
is,
for
but again, it doesn't matter, right? Because we're saying approximately 0. So I'm just gonna do the greater
you
than.
don't care. Okay. And then also I was gonna ask for the first one since it's underweight. Wouldn't we ideally want to find 15.99 rather than 16 since we're
Oh no, we're not gonna do that. Yeah, we're just gonna do the number. Yeah. Just the way probabilities behave, it actually